Lab 3, Circuits, Physics 2212, Griffin Davis. Introduction. The purpose of this lab was to use real circuit equipment to experimentally understand the inner workings of circuits, resistance, current, and voltage. Our results were that the current of the circuit was about 19 milliamps. The resistance of the total wires was 5 ohms. The resistance of the 100 ohm resistor was experimentally 113 ohms. The resistance of the 47 ohm resistor experimentally was 44 ohms. And the resistance of the ammeter was about 6 ohms. The discharge and charge times of both of the capacitors were also found to be approximately equal. The fundamental principles of the lab include Kirchhoff's loop rule, in which all the voltages in a closed loop around an entire circuit sum to be zero. Kirchhoff's junction rule, in which the sum of all currents at a junction is equal to zero, with the current going into the junction subtracted by the current going out of the junction is equal to that zero that was previously stated. And Ohm's law, in which the current passing through a wire is equal to the potential difference of the wire over the resistance of the wire. The first circuit had two 1.5 volt batteries set up in circuit, one multimeter used as an ammeter, and then one multimeter was used in parallel as a voltage reading to help get some of the voltages that we're going to discuss on the next slide. And then two resistors were included in the circuit, one of about 47 ohms and one of about 100 ohms. These are ideal values and not the experimental values that we will also discuss in the next slide. And then our system was made up of the circuit, with the surroundings being everything not included in the circuit. Results. Firstly, the voltage throughout many points of the circuit was found using the voltmeter in parallel with the circuit. Many of the voltages here sum to be less than zero, which indicates large error due to the imprecision of the multimeter and due to human error in the readings. The voltages throughout the circuit were also graphed on this table that you can see in the bottom right. And using these values and the average value for the current experimental resistances were calculated for each of the resistors, the total resistance of the wires, and for the ammeters. Our second circuit included two 1.5 volt batteries, which were used to charge up the 0.2 F capacitor, and two different light bulbs that were not used at the same time but were switched out to help determine some of the different usages and some of the different values for the different light bulbs, one of which was 10 ohms and one of which was 20 ohms. The battery was also taken out during the discharge portion of the capacitor to figure out some experimental values for that as well. And the system was our circuit, and the surrounding was everything else. Results for the second part of the experiment. The 10 ohm bulb was found to charge in 30 seconds and discharge in 31 seconds, approximately equal times. And the 20 ohm bulb was found to charge in 59 seconds and discharge in 62 seconds, again approximately equal times. Also, notice how the time of charge and discharge doubled for a double in the resistance of the bulb. Also, when the natural log of the velocity of the voltage over the initial voltage of the current was plotted against time, we then took the slope and put -1 over the slope to find our RC for the capacitor, which was found to be about 9.51. Errors. Our data seemed to have many errors in its collection, likely due to human error in timing and the inaccuracy of the multimeter. What if you charged a capacitor with no resistor in the circuit? Ideally, the capacitor would instantaneously charge. However, resistance in the wires and the resistance of the multimeter would cause the capacitor to charge slower than instantaneously, as we found to be about 5 seconds in our experimental measures. Conclusion: Kirchhoff's node and loop rules hold firm, and the RC of the 10 ohm bulb was found to be about 9.51. Thank you, Griffin Davis.